Hello, we are from Tech University, and this is a project, and the project name is Design of Low Power High Speed Truncation Error Tolerant Adder. The batchmates are Naveen and Manikandan. Company name is Central Institute of Tool Design. Internal name is Mr. A. Yogaraj. In modern VLSI technology, the occurrence of all kinds of error has become inevitable. By adopting an emerging concept in VLSI design and test, error tolerance and novel error tolerant adder is proposed. The ETA is able to ease the strict restriction on accuracy and at the same time achieve tremendous improvements in both the power consumption and speed performance. The need for ETA is we have to set the huge data and need for instant reply require the adder to be large and fast. This ETA can attain great improvement in both power and speed. And this is a proposed arithmetic addition, and here we have to separate the additional part into two halves. One is your accurate part and other one is your inaccurate part. The accurate part which consists of your conventional adders like RCA, that is ripple carry adder, carry select adder, carry skip adder, and your inaccurate part is actually our ETA. Arithmetic part will do the normal addition from right to left, and that will be our MSB, and accurate part will be our error tolerant adder. And if you get both one as your input, and from there all your outputs will become one. We'll see how it happens. This is the block diagram of a project, and as I shown the last slide, the left side is conventional adder, right side is the error tolerant adder. The half of the input will be given to the error tolerant adder and half of the input will be given to the conventional adder, so that your MSB won't change. MSB will be constant, and your right side will be error tolerant adder, and this is the adder implementation of ETA. Actually, ETA consists of two parts. First part is accurate part, that is constructed using a conventional adder use such as RCA, CSK, CSL or CLA. And second part is inaccurate part, consists of two blocks. One is carry free additional block and second one is control block. This is your control block. Actually, what will happen is that your inputs will be given to the the control blocks is being divided into two types, that is type 1 and type 2. And the type 1 is consists of one AND gate and one OR gate, which will the next control output of the control block will be given to the previous block. For example, if the input of the A0 and AB1 is given to the control block 1, and the output of the next control block, that is A1 and B1, so that output will be given to control block 1, that is type 1. Actually, this is A1, A0 and B0 and this is your output. Actually, the output coming from A1 and B1 will be given to the input for this OR gate. So this is type 1, and type 2 is that we will give next output and as well as the output of the I plus 4, that is if you are giving the input A3 and B3 for the AND gate, and you have to give the output of the control block A4 and B4 and the output of the control block A8 it is A15 and B15. So this is the two types of control blocks actually. And next one is your carry free additional block, and the control inputs will be given to the modified XOR gate. This is our modified XOR gate. So we have modified it by adding a two PMOS and one NMOS and an NOT gate. If suppose the control block is 0, M1 and M2 will be activated and M3 will be deactivated, so that it will do the normal XOR operation. And if the control is 1, so what will happen is that your sum will be your VDD, so the output will be 1. This is about your carry free additional block. and this will be output of your error tolerant adder. This we simulated through the model sim software. So this is the output, this will be the output, and this is our conventional adder, that is ripple carry adder. So this is like we have a full adder, we will give a scene, the output, the carry will be carried to next full adder, so it will go like this. Next one, it's the output of the ripple carry adder, and it is done through Xilinx. The example of the ETA is that, see, that is, it is the ETA output, that is 72863, and the actual output is 72877. The overall error is actually 14, so accuracy is 99.98. So we have to just lose that 0.02% of your accuracy, so that you could gain more speed, and you can save a power. So this is actually our observation. So you can see that the power consumed by ETA is less than all other conventional adders, and delay is also very low, and PDP is power delay product, that is also very low, as you can see, and PDP saving is not applicable, and transistor also we can use only 1006 transistor. So this is the design flow of Verilog in FPGA. Application is that it can be used in DSP applications like related to human sensors, like image processing system, speech processing system, because DSP is full of multiplication and addition. So that in FFT DSP we will use, mostly we will use multiplication addition, so it is the right place to use this error tolerant adder. And conclusion is that extensive comparison with the conventional digital adders shows that the proposed ETA outperformed the conventional adders in both power consumption and speed performance. The potential application of the ETA fall mainly in areas where there is no strict requirement on accuracy, or where super low power consumption and high speed performance are more important than accuracy. Thank you.